Hello, we are back, and today we're going to be talking about local and now global extrema. Maximum and minimums is what extrema really sums up. And then we're going to talk about the first and second derivative tests, which aren't anything fancy, and you've actually been doing one of them for a long time. The other one got introduced because it comes in handy from situation to situation. So we're going to look at through this example here. Determine any possible maximum and minimums of y equals x to the third minus 2x squared. So we can either do this by hand, in which we could rewrite this as x squared x minus 2, in which you know that the graph will have a 0 at 0 and at 2, and the sketch of the graph will look something like this. And if I put this into the calculator, which I already did, notice that's very similar to what we have. Right? Not perfect, but it's a sketch. Now, we can see from this graph that there's going to be a maximum and a minimum around these locations. But let's do it with calculus because that's where I want you practicing. So we would look at the derivative of this function, because we'd say y prime is equal to 3x squared minus 4x. And then we look at when these are 0, because you want to know when the first derivative is 0, when that changes from slope, changes direction slope either positive to negative, or negative to positive, where that changing point, the slope would be 0 there. Or you can see it on a graph here. Why am I doing it with a pen when I can show you here? But at the max, the slope will be 0, and at the minimum, the slope will be 0. Okay. And here we would have that if you factor on x, you'd have x, 3x minus 4. So what we would know, if I make a number line here of y prime, is that we would have a 0 at 0 and at 4/3. And if I find out what's happening in each interval, well, let's see. If I plug in -10, you'd have a -10, you'd have negative, and the -10 would make that negative, so those are positive, which you can see that graphically, these all have positive slopes. And then between 0 and 4/3, say I plug in 1, because that's between these two, you'd have a positive number, and 1 times 3 is 3 minus 4, would that be negative? And you can see on the graph that those are negative slopes. And then after, say I plug in a large number such as 10, be it positive and positive, which multiplied together gives me a positive. So what I can see here is that, from what we've done before is we can say, okay, well, 0 here is going to be a local max because it's changing from positive to negative. And 4/3 will be a local min because it's changing from negative to positive. Well, what we've done here, and what we've done all along, this is the first derivative test. Right? And that works more times than not. It just sometimes can get difficult in a way. Sometimes it doesn't always work. Where the first derivative test, which is what we've done, is you want to find when the derivative equals 0, and if the derivative, changes from positive to negative, or if it changes from positive to negative, you'd have a max. And if it changes from negative to positive, you'd have a min. Seen here, like if I was to sketch these, you can see that you'd have a maximum and a minimum. Okay, and that's what we've done all along as a first derivative test, just looking purely at the first derivative to find everything else. But there's actually a second possible way, is another method that comes in handy sometimes, is called the second derivative test. And the second derivative test can also help you get maximum and minimums, where you need to look at critical points. So at critical points, which a critical point again is when f prime of x equals 0. So that as a way, or that's when f prime of x equals 0. So it's still the same idea there. It's when the first derivative is 0. So at these points, if your second derivative is positive, well, let's make sense of this. So if your first derivative is 0, that means your slope is 0. And this is, I'm going to be sketching f of x right here to help you see this. The slope is 0. And if your second derivative is positive, well, that, remember, means that's concave up, which would look something like this. Well, notice, what does that tell you? Well, then f of x is a local minimum. And that's another way of determining minimums and maximums, is looking at still the critical points. You still need to look at the zeros of the first derivative, because those are the slopes of the function. And then you just say, okay, at the second derivative, if you plug in that number, it's concave up, then that's a local minimum. And similarly, if f prime of x, doubled prime of x, is negative, so picture it being concave down, right? That's concave down. Well, then you'd have a maximum. And that's the second derivative test. And they both work just fine. I think first derivative works more often than not. I think this is more successful, or applicable is a better word. But sometimes the second derivative test does come in handy depending on the problem, and you do want to be aware of it. Now, if we were to apply this here, let's just see what happens. So I'm going to do it in red here, second derivative test in red. So then we look at the second derivative, y double prime, which would be 6x minus 4. Well, notice if I plug in 0, so y double prime of 0, if I plug that in, I would have negative 4, which is negative. So picture, concave down. Well, then you have that implies that x equals 0 is a maximum, local max. For the same reason we talked about down there. If it's negative, then it's concave down, so you have a local max. And if I would have plugged in 4/3, well, 4/3 times 6, would be 8, and 8 minus 4 is 2, and that's positive. So I have a concave up feature here, which would imply that at 4/3, you have a local minimum. And that's applying the second derivative test. So that's part of this lesson. And the other part of this lesson is the idea of that word global. All right. Now, why do we talk about the word global? So local is, it's neighborhood, it's community. And in this problem, notice that I called 0 a local maximum. Wait, 0? How come I keep getting 0? Did I mess up my graph somehow? Let me look here. I did mess up my graph. Oh, yeah. I hope you didn't catch this mistake way early in my video and you're like, oh, I can't keep watching this video. It's all messed up. Yeah, it is all messed up, isn't it? I apologize. Should look like at 0, it's a max, and at 4/3, it's a minimum. So it would look something like this, actually. Oops, my bad. And I don't want to redo this whole video, so we'll just keep going from here. Yeah, so 0 and at 4/3 right there, you have your minimum. My bad, everyone. Hopefully I haven't lost you and you're still with me. But a local is in your neighborhood. So we called 0 here a local maximum because we're talking in its surrounding neighborhood. If we just look around it, which I want to do lightly, it's the highest point. So locally, in its surrounding neighborhood of points close by, it's the highest point. Just like locally at 4/3 at its neighboring points, it's the lowest point. Now, global means on the entire domain. All right. So in this problem, if I would have said, and I'm going to zoom out just slightly because I want to make sure you still have the graph visible. So if I would have said here, example 2, what's your global max on the domain -infinity to infinity? Well, notice if I look at the entire domain of this function, well, 0 is no longer, x equals 0 is not a global max, because clearly it gets beyond 0. In fact, it gets beyond 0 starting at that point and higher. It's already, it has a higher y value. So it's not global max. In fact, here there is no global max of this problem if that's your domain you're looking at. Same thing with minimums because it goes down forever. But say it defines a different interval. So let's say, for example, we say what's the global, and I'm going to use the word extrema now, on the interval from -2, or let's go -1 to 3. So now from -1 to 3, if I highlight this on the graph to help you see this, we're looking at from -1, which is here, all the way up to 1, 2, 1, 2, 3, which is here. So we're going to be looking at the curve, this entire part of the curve, which I'm going to try to highlight in red. Now, what's your global extrema? What's the maximum and the minimum of the entire domain there? Now, the trick with these, and I'm going to highlight this, is you still have to find the critical points. So you find all critical points, which is what we did previously, which in this problem is 0 and 4/3. So that's when f prime of x equals 0. So here that's x equals 0 and 4/3. And you still evaluate there. But what you also need to do, very, very important, 3-star general, is that we have to evaluate on the endpoints of your domain. I'm going to highlight that. Right. So there's two things you have to do when you talk about globals. You have to, 1, find the critical points, and 2, very important, you always look at the endpoints, which the endpoints here are -1 and 3. So if I make a table here, I'm going to zoom in now, and we're going to finish this problem together and be done. So what's the global extrema on this domain? So I make a table x, comma, y, and we're going to look at -1, 0, 4/3, and 3, those 4 values. And we know at 0, well, I don't think we ever figured it out. So let's plug this in. And we know that y is the curve x to the third minus 2x squared. Okay. So 0 and 4/3 were critical points. If we plug 0 in, we have 0. If we plug -1 in, I'm going to use my calculator or just do this, make sure my math is right. Well, -1 to the third is -1, minus 2, and then -1 to the number is positive, so that's just -2. So -1 minus -2 is -3. And at 4/3, that one I need a calculator for, 4/3 to the third power minus 2 times 4/3 squared. Well, that gives me -1.185 approximately. And if I plug in 3 into my calculator, and there's my calculator right there. If I plug in 3, so 3 to the third minus 2 times 3 squared, well, then I get 9. So notice now on this domain, what's my max, my global max, my global minimum on this domain? Well, my smallest value is now -3. So now this -1, -3 is my global minimum. And notice that at 3, 9, that is now my global maximum. So earlier in this problem, we were saying that 0 and 4/3, if I scroll up just a little bit, we were saying 0 and 4/3 were the local max and local min, and that's true. In its community, in its surrounding points, it's the highest point, lowest point. But when we talk about global extrema, if they ever ask you and they give you a domain, and they, by the way, they have to give you a domain. They have to give a domain. Or you would assume it's the entire domain negative infinity, which doesn't always work out nicely in those problems. But on that domain, not only do you look at the critical points, you also have to evaluate the endpoints on the domain, which in this case were -1, 3. And in this case, I designed it in a way where those were the global min and global max, not the points we found previously. And you can see that, lastly, piece it all together, you can see it on the graph. Clearly, this point right here is a lower y value than this point here. So there's your global min, and that might be a local min. And on this domain, you have your local max, but on this domain here was your global max. All right, and I don't know if you can see that, so I'll zoom in and end on that point. Okay. If you have any questions, feel free to let me know. I know your problems will help you explore this yourself on your own problems. If you need any help, just don't hesitate to reach out. All right, bye-bye.